Hello, everybody. This video about the Fubini's theorem for the course Maths 2019. That's for the University of New South Wales. Today we are going to talk about Fubini's theorem and do some examples. Fubini's theorem, there are two types of integration. So here we have A and B. So A and B ranges for the x. So in this situation, x will be the constant. And the range for the y is the lower curve will be the alpha x and the upper curve for the beta x. So we can write this range as D, the domain consists of x and y's, the pair of x and y's. And A, x ranges from A to B, and y ranges from alpha x to beta y. Fubini's theorem is to write it down this type of integration to this type of integration. So it's swapping the dx and dy, basically. In order to be able to do that, the function is not really relevant in some sense, as the region is the key important. We need to understand what the region is, and then we would like to rewrite the region into another type. So this is why I'm talking about the two types. So the second type, so first let's finish the first type. So what it means. So x is a constant. So for example, x is equal to a is a constant. The line x is equal to a line, x is equal to b line. So there's the constant terms. And in this range, when we are looking at from this direction, the lower bound will be the curve alpha x, and the upper bound will be the curve beta x. So this is how we read. So think about a flow from this direction to this direction as x constant. In that direction, you hit first alpha x, that is your lower boundary. Then you hit beta x, that's your upper boundary. On the other hand, if you want to turn, for example, this one to this one, but the regions will be the same. So I'm doing it is just a definition of the two types. When you will see in the exercise, we have the same region. We are converting the regions by reading to another type. So D is X and Y, and C and D ranges for the Y, and gamma Y and delta Y ranges for X. So in this case, Y is a constant, C is equal to Y is a constant, Y is equal to D is a constant. So the Y is equal to D line, Y is equal to C line, they are constant. In this case, we are thinking like a flow coming from this direction. So you hit first alpha y, so this is why you have the lower boundary, and the upper boundary you hit second will be the delta y. So this lower bound and lower bound. It will make sense when we are doing more exercise on it. Let's do the question 65. Now we would like to use a double integration to find the area, the region bounded by root x, y is equal to x, and y is equal to x over 2. Now for this question, we would, you have three curves, and you want to decide exactly the region. You're interested in the intersection points of those because the area that you're interested in is defined by these curves. So the intersection points will be the where possibly that the type of the curve boundary will change. So if you have y is equal to root x, y is equal to x, these two intersection of these two curve will be x is equal to x squared. So you have two things, x is equal to 0, x is equal to 1. So x is equal to 0 is 1 point for the point of x intersection, and x is equal to 1 is another point of intersection. So if this is y is equal to root x curve, and y is equal to x curve, and this is y is equal to x over 2 curve. And if you look at the intersection y is equal to root x and x over 2, then you have x squared over 4. When you solve this little equation, you will have x is equal to 0 and x is equal to 4. So you have one intersection point corresponding this point and one intersection point corresponding that one. So you want to find out what is the y when x is equal to 1, what is y? When x is equal to 4, what is y for these curves? Sorry. And if you put for the other curve, x is equal to, y is equal to x and x is equal over 2, and we don't need anything because we know that they intersect x is equal to 0, so there's no need for it. Okay, when x is equal to 4, y is equal to 2. That is where this one is coming from. And also if you put x is equal to 4 and y is equal to 2 for this point. So this point of the intersection is the intersection of the curves of this one and this one. So we decide exactly the region now. So the region is this colored area, this one and this one, right? This one and this one. But the thing is that this region have a different feature. From here, from 0 to 1, for x is 0 to 1, you have this curve. Lower boundary is x over 2, and upper boundary y is equal to x, which is this green area. After x 1 point, after this point, x is equal to 1, y is equal to 1 point after this line, or x is equal to 1 line, then the feature of the boundary of the curve is changing. One of the lower boundary becomes y over x, and upper boundary becomes y over root x. So if we want to write down that as a mathematical way, so the region will be xy. From 0 to 1 for x's, we have lower bound y x is over 2, and upper bound y is equal to x, which is the green one, which is this green area. So this was the first one. This one represents that green area. And this area, this is the union of all points satisfying this condition. That is from 1 to 4, and that is for the x's, x ranging from 1 to 4, and y ranges from the lower bound curve is x over 2, and upper bound curve is root x. So that's that one. We want to find out the area. So that's 1 of dA on the region. So the region is from the 0 to 1. Since this is a union of two sets, we need to calculate two integral corresponding each part. This one is from 0 to 1. X is the constant. So this is why we have x is the out integration. Inside integration is the y. This is the lower bound. That's the upper bound. For this one, again, x is a constant. So x is the upper outside dx, the outside one. And the inside is the changing from x over 2 to the root of x. So, and we want to calculate what area. So the function is just simply 1. If we, from here to here, y, it will be just the dy, integrations of dy is just y. So upper bound is x minus the lower bound. Again, from here, y and the upper bound minus the lower bound. Here you have 1 over 2x. Taking the 1 over 2, we have only x. Here we have, we can separate 2, root x. The integration of root x is 2 over 3, x3 over 2. And here we have 1 over 2. And then the x will be 1 over 2x squared integration. And substituting this will be 1 over 2x squared when we integrate x. substituting the one over the boundaries with the numbers. Then we have 1 over 4 from here. We have 2 over 3, 7 from this side. 1 over 4, 4 squared minus 1. All together, just making the denominators are the same. We will find eventually 7 out of 6. I think this part is just everybody come to the subject for this class, basically, to be able to write it down the region. That's the key idea for this exercise. Now, here we are looking at this integral. What is the region? The region here is given by, just by reading, the y will change from 0 to 1. Right? This is the y changes from 0 to 1. And x changes from y to 1. X changes from the y to 1. So y is a constant. It means that we are looking at the flow over this direction. Y is equal to 0 is the line, is this line. This line, actually, y is equal to 0. And then we have y is equal to 1 is this line. So y is a constant. And then the reading says that first you will hit the lower boundary of the curve is y is equal to x. So this is the lower bound, and y is equal to 1 is the x is equal to 1 is the upper bound. So from here to here, here to here, here to here. So you're looking at this triangle, this part from this part, and then you're hitting first to this curve and then hitting x is equal to 1 line. So it means that this area is the area that you're concerning with. Okay, now we would like to, so this is the y constant. We would like to turn everything into the x constant because we would like to apply the Fubini's theorem. We would like to change the order of the integration. Then, so the y constant will be the x constant. Same region. We are thinking about the same region, but this time you're looking at the flow from this direction, from up to there. This region, for the x purposes, ranges from the 0 to 1. Yes, 0 to 1. This is why I have 0 to 1. And then first, because we are dealing with this little region, this one here, y is equal to, x is equal to 0 line. This line is x is equal to 0 line. And this one, x is equal to 1 line. So y is equal to 0 line is this one. Y is equal to x is this line. So the lower bound is this one, y is equal to 0. And the upper bound, y is equal to x. So this is why I have this equation. You're looking at the flow from this direction because we are making the x are the constants. The x region is 0, 1. And the y region will be this is the lower curve from here to here, which is the y is equal to 0 curve. And then y is equal to x curve is the upper bound. Y is equal to x curve is the upper bound. So this region and this region are exactly the same, but the two different readings. We are turning type 2 to type 1. Then we can change order of the integration. So this is the original one that we got, which is corresponding that one. 0, 1, changing over 1, y1, and fx, we are not touching fx, y. And then we have this region from 0 to 1, that will be dx outside. And for the y changes from 0 to x, just that one. So these two integrals are equal. That's the Fubini's theorem. If you decide your region and read another type, then you can interchange the order of the integration. That's all about the Fubini's theorem. Up to this point, after that, it's just the integration. So first, here you would integrate x. Now we would integrate y, then the integration of y, x will be a constant here. It's just y. So this is from the 0 to x. If we put the x here, we have 0 to 1 e to the x squared x dx. So if you have x squared is equal to u, 2x dx du, if you change this variable, you need to look at how this boundary change. X is equal to 0, u is equal to 0, x is equal to 1, u is equal to 1. So that is 1 over 2 comes from here. Du over 2 is x dx. X dx is 1 over 2 du. And this one here, just e to the u, that is 1 over 2 e to the u 0 to 1. If you put the e to the 1 minus e to the 0, e to the 0 is 1. So you have 1 over 2 e minus 1. Again, the key idea in this exercise for this class is really to decide this one. So you need to be very comfortable with the integration method. Yeah, please check yourself. Please exercise more. Remind yourself about the integrations. Okay, let's have a look this question. Integral here is minus 1 to 1 x squared 2 minus x squared. So did I do? Let's decide the region first of what this one says. So x is outside. It means that you have that ranges from minus 1 to, this is minus 1 to plus 1. And y is equal to x squared, and y is equal to 2 minus x squared. Y is equal to x squared, this curve. Y is equal to 2 minus x squared is this yellow curve. So the region is this blue area. And now, since we are reading with respect to x, we are looking at from this direction. That's exactly what this region is. So the lower bound is x squared and upper bound 2 minus x squared. Now we are going to read this region and the other type in the other way when y is constant. So if y is a constant, you're looking at from this direction. If you look at from this direction, y changes from 0 to 2. But when we are changing from 0 to 2, you have two regions are appearing here. One of them is when you're looking at this area, your first lower bound is here and upper bound is here. And when you look at this area, your lower bound is this curve and upper bound is this curve. So what I'm saying is that, so you need to think about the y from 0 to 1 and then 1 to 2 as two different regions because the lower bounds and upper bounds are different. From 0 to 1, then you will have square root of, so x will be square root of y minus plus. So this will correspond to minus sign, and this one will correspond to plus sign. So this is the lower bound, and this is the upper bound. You're looking at from this direction. So you hit first this one, and then that one. So this is why you have root minus y and root y. And then when you look at the region for y is equal to 1 to 2 for this one here. So the yellow curve, this part of the yellow curve is a square root of, right? Because this one here, y is equal to x minus x squared. Then we take this one over here and this one over here, and then the square root will give you x is minus plus square root of 2 minus y. So you have minus square root of 2 minus y is this one as a curve, and plus square root of 2 minus 1 is this curve. So for this upper hemisphere, upper half of this half circle, you will have y is from 1 to 2, and then you have this curve, lower bound is minus a square root of 2 minus y, x and 2 minus y. It's the same region. This is exactly the yellow. But when you look at this one, so you have this curve and this curve, and you look at from this side, you have this one and this one for this region, and the union of this one, this lower bound and upper bound. So this is what it says. So this gamma, the region, that's the union of this x and y pairs satisfying this condition and x, y pairs are satisfying this condition. Once we wrote down, the region is just, we can interchange the order of integration. So let's say I1 is the integrations in this one. I say this one is rho 1, sigma 1, sorry. And this one is a sigma 2. So first look at the sigma 1 of the integral of dy dx. And, since we are changing the order, that will be dx dy. This means the y is the constant. This is what it says, 0, 1, y. And x will change from minus root y to the plus root y. Then integral of this is just x itself. Upper bound minus the lower bound, that will be 2 root y. And then when we integrate this one again, we will have 2 is here, 2 over 3y, 2 over 3. From 0 to 1, that's 4 over 3. This should be 1 here. Okay, and the second part from 1 to 2, and a square root of minus root 2 minus y, square root 2 minus y. Again, the x integrate of the x is just the x itself, lower bound, upper bound. So we will have 2 constant as it happened here. And when we integrate again, we need to change the variable because this time we have 2 minus y. If you take 2 minus y is like equal to u, and minus dy is equal to minus u. Y is equal to 1 is equal to u is equal to 1. Y is equal to 2, u is equal to 0. So we have minus 2 root 2 from 1 to 0 now. Now if you change the order here, that will be minus minus, so that will be plus. And we integrate, and then we will find 4 over 3, as we've done here. Okay, and so the whole integral will be the addition of these two integral, 4 over 3 plus 4 over 3. It's 8 over 3. That's all for this part. Thank you very much. I hope this is helpful for you all.